In this lesson we're going to compare the magnetic properties of iron and steel. To help explain their differences, we have to understand that both the structures of iron and steel, and with any other metal for that matter, are made up of what is called crystal grains. That's to say, there are millions of crystal grains running throughout the structure of the metal. Okay, so if we were to look at the surface of iron under a high-powered microscope, the crystal grains would appear something like this. Now, these crystal grains run throughout the entire sample, and the region where one crystal grain meets another is called the grain boundary. Okay, so this is the grain boundary. And before we go on to talk about magnetic domains, let's look at the crystal grains we find in a sample of steel. Okay, so you'll notice immediately that these grains are a lot smaller than those in iron. Now, the reason for this, we've got a sample of iron, it's a sample of pure iron or wrought iron, and because these grains are larger than those for steel, it's actually easier to work iron. Iron is more malleable. You can hammer it and shape it easier than you can with steel, which is a harder substance, as you know. Okay, so steel is actually an alloy of iron and carbon. So it can have, depending on the type of steel, anything up to about 4% carbon in the structure. So it's precisely this carbon, if you like, or impurities, which cause the crystal grains to be smaller. Okay, so there are more grain boundaries in a sample of steel than there are in a sample of iron. The fact that these grains are smaller in steel, again, means that steel is a harder, tougher substance than iron. It's harder to hammer into shape. It's less malleable. So physically we can say that iron is a softer material while steel is a harder material. Now, it's important here to distinguish between the crystal grains and the concept of magnetic domains, which we were talking about earlier. Okay, so we can represent the magnetic domains in this sample of iron, which at this moment is not magnetized, and we'll represent those domains by these red arrows. Okay, and so it's not magnetized, and the arrows can point in any random direction. And each of these arrows represent the magnetic field which are produced by the magnetic domains which are inside each of these crystal grains. Okay, now if we look at the steel sample, well, we'll draw those same magnetic domains in the steel sample. Again, at this moment the steel is not magnetized, so just like in the iron, the magnetic domains are pointing in random directions. So the net sum of the magnetic fields in this sample is 0. Likewise, the net sum of the magnetic fields in the sample of iron is 0. Now then, what happens when I apply an external magnetic field to either of these samples? Well, the important difference is here. Because the crystal grains in the iron are larger, the magnetic domains have more freedom to realign themselves with the applied magnetic field. And it's much easier to do that in the case of the iron because the grain sizes are greater and there's more freedom for the domains to reorientate themselves. Now, in the case of the steel, there's less freedom for the domains to align themselves in the direction of the applied field. So, because these have got smaller grains, crystal grains, now emphasize, I'm not talking about the domains here, I'm talking about the grain sizes, the crystal grain sizes. That makes it harder for these domains to align themselves with the external magnetic field. So what we're saying is, because iron has bigger crystal grains, it means it's easier to magnetize than steel, which has smaller crystal grains. So steel is harder to magnetize, but because iron is easier to magnetize, then it is also easier to demagnetize. So once you remove this external magnetic field, the iron will lose its magnetism. The magnetic domains will randomly orientate themselves again. Whereas in the case of steel, if you remove the applied magnetic field from a steel sample, then once it's been magnetized, it tends to retain its magnetism. So it's harder to demagnetize a sample of steel than it is a sample of iron. Okay, so these magnetic properties of iron and steel are quite easy to demonstrate using a very simple experiment. what we've got here is a permanent magnet, and we're suspending, using magnetism, by magnetizing iron tacks, we're suspending a chain of iron tacks from one end of the permanent magnet, from the north pole of the permanent magnet, and then from the south pole, it doesn't really matter which you use, and then from the south pole of the permanent magnet we're suspending a chain of steel paper clips. Again, making use of the fact that each paperclip magnetizes the paperclip beneath it, and so you can connect up, depending on the strength of the permanent magnet you use, you can connect up quite a long chain of paperclips, maybe 7 or 8 paperclips actually in total. Okay, so once you've got these two chains suspended, what you then do is you carefully remove the two chains from either end of the magnet, holding this paperclip and holding this tack, and what you'll notice immediately is that as soon as you do that, the chain of iron tacks immediately collapses, because as soon as the external magnetic field provided by the magnet is removed, the iron loses its magnetism, whereas the steel paper clips retain their magnetism, and so the chain remains intact. You can still suspend the paper clips with your fingers even when the magnet isn't there. Okay, so we have a special term which describes the magnetic properties of iron. We say that it is magnetically soft. A magnetically soft material is a material which can be easily magnetized and easily demagnetized. So iron fits into that category, whereas steel, or stainless steel, as in the case of these paper clips, is said to be magnetically hard because it is harder to magnetize, and when an external magnetic field is removed, it still retains its magnetism. Now, if you want to make a permanent magnet, for example, well, that's exactly what you want. You want the thing to retain its magnetism once the external magnetic field that is used to make the magnet is removed. Okay, we'll look at how you make permanent magnets in a later lesson. So you want magnetically hard materials to make permanent magnets. Although on saying that, although steel does retain its magnetism, there are other materials which are far better at retaining their magnetism. For example, ferrite materials or modern day magnetic materials such as neodymium or alnico. Magnetically soft materials have a distinct advantage over magnetically hard materials in that you can use them for two particularly important applications, which is that of making electromagnets and for making the core of transformers. So these diagrams show schematics of an electromagnet and of a transformer, and we'll talk in detail about both of these devices in later lessons. What we're looking at now is the material from which the cores of both devices are made. Okay, so just briefly, when we switch the switch on the electromagnet, a current will flow around the solenoid which magnetizes the core material inside it, and what is important in the case of an electromagnet is that that core material magnetizes quickly, and equally important when we open the switch that the core material demagnetizes easily. Okay, you don't want the core material to retain its magnetism because you want to be able to drop the object that you're carrying. So just emphasizing again, the core of the electromagnet must be made from a magnetically soft material. And the best candidate for this is pure iron, or soft iron as it is also known. So exactly the same thing applies to the core of the transformer. Okay, in this case we have a 50 Hz AC current going into the primary coil of the transformer. What that's doing is it's magnetizing and demagnetizing the transformer core 50 times a second. So again, the same applies. You don't want the core retaining its magnetism. You want it to be able to gain and lose its magnetism easily 50 times a second. So again, you can't make either the core of the transformer or of the electromagnet out of a magnetically hard material such as steel, because it will retain its magnetism. In fact, that will cause the core of the transformer to heat up. Okay, so the ideal material for the core of an electromagnet or a transformer is soft iron. Okay, a core made from pure iron and not from steel.